Welcome to This Explainer, everyone. Today, we are going to completely transform the way you approach Cambridge IGCSE physics graphs. I know exactly what happens in the exam hall. You open your 0625 paper, flip the page, and there it is, a massive, intimidating grid staring right back at you. Too often, we look at these grids and just see abstract math, a totally tedious chore to decipher, or a place where students completely overload their answers with raw facts, but miss the actual analysis. But today, we're changing that entire narrative. We are turning those abstract dots and lines into dynamic, living stories about the physical universe. Whether it's tracking the motion of an Olympic runner, measuring the extension of a spring under a heavy load, or mapping a parachutist in freefall, these graphs aren't just lines. They are literal blueprints of reality, and mastering them is your ultimate strategy for securing those top marks.
So before we even think about calculating anything, before you instinctively grab your calculator or rush to scribble down an equation, we have to stop and ask ourselves, what is the physical reality behind the ink on the page? Because here's the secret to Cambridge exams. Every slope, every curve, and every single intersection is a piece of hard evidence showing us exactly how the universe behaves. Examiners don't just want a number. They want to know if you can translate that math back into the real world. Our job today is to build your physicist toolkit so you can read that evidence flawlessly, every single time.
To get you there, we've broken this down into 5 crucial areas. We're going to cover the language of graphs, reading between the lines, straight line secrets, intersections and areas, and finally, decoding the curves.
All right, let's jump right into Section 1, the language of graphs, where we'll understand the 4 foundational relationships you absolutely need to know.
Now, in your exams, there are 4 basic relationships you're going to encounter, and recognizing them instantly is a massive time saver. First up, we have a positive relationship. This is your classic upward slope, showing that as your independent variable increases, your dependent variable increases too. Simple enough, right? Next is the negative relationship, shown by a downward slope. One goes up, the other goes down. Then, we get to a really special case, directly proportional. Examiners absolutely love testing this. It's not just a straight line. It's a straight line that passes exactly through the origin. This means if you double one variable, the other variable doubles exactly. It's a perfect one-to-one scaling. Finally, we have the inversely proportional curve. This is that sweeping curve, where if you double one variable, it cuts the other exactly in half. Recognizing these shapes on sight is step 1 to decoding the question.
The absolutely crucial takeaway from those foundational shapes is what a straight line actually represents. A straight line means you are looking at a linear relationship. This means that as your independent variable on the x-axis changes in equal, predictable steps, your dependent variable on the y-axis changes equally too. It's steady, it's reliable, and it's incredibly useful for finding patterns when you're under the pressure of a ticking exam clock.
Moving right along to Section 2, reading between the lines, where we'll extract hidden data using interpolation and extrapolation. But before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, so in practical physics experiments, we often only have the time or the equipment to take a very limited number of readings. We plot our points, but what about the spaces in between, or the space beyond? While interpolating is the process of finding values hiding inside our existing data points, extrapolating is like having a crystal ball. It allows us to predict the future of a trend. By extending our line of best fit, we can estimate values we haven't even measured yet. But here's where students lose marks. You must use your physicist's intuition to judge if the trend will logically continue. For instance, you wouldn't extrapolate the speed of a sprinter indefinitely, because obviously they are going to get tired and slow down. But in tightly controlled scenarios, extrapolation is a brilliantly powerful predictive tool.
To extrapolate effectively and secure those method marks, just follow these 5 bulletproof steps. First, always read your axes to ensure everything matches up. Second, grab your ruler, never do this freehand, and extend the graph's trend line using a dashed line. Third, draw a perfectly horizontal line from your new target value on the y-axis until it intersects your newly extended trend line. Fourth, drop a vertical line straight down from that intersection to the x-axis. And finally, step 5, do your subtraction to find the difference between your initial value and your new one. It's a mechanical process, but it works every single time.
Let's apply those exact steps to a real-world scenario. Look at this distance time graph tracking the incredible sprinter Christian Coleman. The graph shows he ran 100 meters in exactly 9.6 seconds. But what if a question asks you to predict his time if he ran an extra 20 meters at that exact same average speed? Don't panic and start writing out massive equations. Just use the graph. We extend our grid, take our ruler, and draw that dashed line up to the 120-meter mark. We draw across, drop the line straight down to the time axis, and boom! We find it would take him 10.7 seconds. Subtracting his original 9.6 seconds from that 10.7, we instantly see it would take him 1.1 seconds to cover that additional 20-meter distance. You've solved a complex prediction scenario visually with zero complicated algebra required.
Let's transition into Section 3, Straight Line Secrets, where we unlock the hidden power of equations, gradients, and intercepts.
Listen, every straight line graph you will ever see holds the famous general equation y equals mx plus c. To find m, which is the gradient or the steepness of the line, we simply divide the vertical change by the horizontal change, the classic rise over run. You pick 2 points on the line, find the difference between their y-coordinates, and divide that by the difference in their x-coordinates. A quick pro tip for your exams. Always pick 2 points that are far apart on the line. It drastically reduces your margin of error and keeps the examiners very happy.
But remember our core philosophy today. As physicists, we care about what that number actually represents in the real world. A gradient is never just a random number. It tells a physical story that depends entirely on your axes. And this is a massive trap that catches out so many students. If you calculate the gradient on a distance time graph, congratulations, you've just found the object's speed. But if you calculate the gradient on a speed time graph, you've discovered its acceleration. The exact same mathematical operation of dividing the y change by the x change reveals two completely different physical properties. Always check your axes.
Here we see this concept beautifully in action. We are measuring the extension of a spring as various weights are added. We take the change in length and divide it by the change in load to find a gradient of 1 centimeter per newton. Since load is essentially a force, we use F as our independent variable on the x-axis. But notice something super important here. The line doesn't start at 0. It actually starts at 3 centimeters on the y-axis. That intercept right there, that's our c value from the equation. It represents the original unstretched length of the spring. So our abstract math class y equals mx plus c suddenly transforms into a real-world physical equation. Length equals force plus 3. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 great boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Now let's tackle Section 4, Intersections and Areas, where we solve complex, multivariable scenarios.
Imagine a grueling 4,000-meter race featuring 2 athletes, runner A and runner B. If we track their progress on a distance time graph, eventually those 2 lines are going to cross. Now, when you see 2 lines intersecting like this, you have to realize it is not just a crossing of ink on a grid. It represents a dramatic, dynamic, physical event happening out there on the track.
So, what is the specific terminology you need to use? An intersection means both subjects are at the exact same place at the exact same time. On this specific distance time graph, it means runner B is physically overtaking runner A at that precise minute and meter mark. The graph is literally giving you a high-definition snapshot of the most exciting moment in the race. Whenever you see lines cross, look down at the time axis, look across to the distance axis, and you know exactly when and where the action happened.
Now here's a concept that is practically guaranteed to show up on your paper. On a speed time graph, the distance traveled isn't represented by a line at all. It's actually the area hidden completely underneath the line. Why? Because distance is simply speed multiplied by time. So to calculate the total distance our runner traveled, we systematically split that weird shape under the graph into measurable, basic geometric shapes. Let's break it down. First, we find the area of the first accelerating triangle, which gives us 150 meters. Then we calculate the area of the constant speed rectangle in the middle, which is 300 meters. Finally, we calculate the area of the decelerating triangle at the end, which is 50 meters. Add them all together, 150 plus 300 plus 50, and we can confidently state the runner traveled exactly 500 meters. Showing this geometric breakdown is exactly how you secure maximum marks.
Finally, let's dive into Section 5, Decoding the Curves, Mastering Changing Gradients, and the Concept of Terminal Velocity.
Up until now, we've dealt with straight lines. But tracking a parachutist's entire journey, from jumping out of the balloon to landing safely on the ground,
creates a beautifully complex curve. While a straight line on a speed-time graph means constant acceleration, the constantly changing shape of a curve tells us exactly what is happening to their acceleration second by second, as air resistance vigorously fights against the pull of gravity. Let's build this narrative step by step, exactly how you would write it in a long answer question. At the very start of the fall, we see a steep slope, which means high acceleration, as gravity pulls them down. But as their speed increases, air resistance starts building up against them. You can see this visually as the curve begins to flatten out, their acceleration is lowering. Then the line goes completely flat horizontally at the top. This is the crucial moment. They have hit terminal velocity. The forces are balanced, their speed is constant, and acceleration is exactly zero. Then we see an incredible physical event on the graph, a massive, sharp downward drop. This isn't a mistake. This means the parachute has just been deployed, causing a massive amount of air resistance and high deceleration. This rapid slowing down eventually levels out into a new, much lower flat line. This is their new, safe terminal velocity. Finally, the line drops vertically to zero on the axis as their feet hit the ground and they come to a complete stop. The entire dramatic journey is perfectly, elegantly captured in a single, continuous line.
Once you train your eye to read these curves, you can identify physical events instantly. Look at these variations. A steep, straight downward line, that's a car braking hard with uniform deceleration. How about an upward curve that starts flat and gets steeper and steeper? That's a rocket firing its second stage burner, drastically increasing its acceleration as it burns off fuel mass. The curve never lies. Whether it's a gentle slope or a jagged drop, the shape of the curve always reveals the absolute physical truth of the object's motion.
So, I want to leave you with this final thought. Graphs aren't just tedious math chores designed to test your patience during an exam. They are elegant, highly detailed maps of the physical world, just waiting for you to read them. They tell thrilling stories of speed, of opposing forces, of dramatic races, and of objects falling from the sky. The next time you sit down in that exam hall and are faced with a blank grid and a plotted line, take a breath and ask yourself, what is the physical reality hiding here, and what hidden story are you going to decode? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.